I started.
I think we started recording. Okay, cool. Well, hello, everybody. Welcome to the Open Team web series. Today we have with us Aaron Ault from the Open Ag Tech and Systems Center here at Purdue. So my new colleague. And I'm very excited to have him speak with us because he'll be describing both a couple of different things going on within the OATS Center, but also specifically taking us in a little journey through a couple of the different projects, including, I'm hoping, the Open Ag Data Alliance and all of the different pieces that are available through the OATS sort of ecosystem of tools for us to play with as we begin to think about interoperability within our community. And with that, over to you, Aaron. Oh, and I'm going to start with a little how to find us intro.
Okay. Yeah, so Greg asked me, I think it was Greg, right? Yes? Okay,
yes,
Greg?
correct.
Yeah, it was Greg.
Thanks, Greg. So Greg asked me to show everybody, if you're looking for what upcoming webinars we're going to have or the videos from the past webinars, you can go to gotech.org here. 1T, not 2. That one's $4,000. And you can click on web series schedule over here and you get this calendar. And if you hit agenda, it just kind of has them listed in order and the past ones will be in here. Oops, I scrolled too fast.
The past ones are under web series in the videos section.
Oh, there's a video section.
Web series, drop down, up.
Oh, that one.
Yes,
Okay.
you got it. Videos.
Look at that. Okay.
Success. Thank you, sir.
Excellent. All right, thanks. Okay, so now we'll hop over to the stuff I prepared for today. So as Ankita mentioned, my name is Aaron Ault with the Open Ag Tech and Systems Center, because as OAT is a great part of an acronym for anything open source and ag, whether it's GOAT or OATS, either way. And so I'm just going to give you guys a quick overview about what we do here at Purdue in the OATS Center and the kind of things that we work on. And hopefully when we're done, you guys will have a rough overview of the sorts of projects we've been working on, but then hopefully the last half we're digging in a little bit more technically on the API, some of the API work that we do to help put out there sort of what kind of projects we work on there. So first, just a little bit about me, so you know where I'm coming from. I'm a farmer myself. This is an overhead view of my farm. I've got about 3,000 cows, beef cows over here in these barns, and I've got about 3,200 acres of corn and soybeans that is really my day job during the week and the weekends most of the time. But then I'm also, got my graduate degree in electrical and computer engineering here at Purdue years ago. So I'm a software developer and coder, and also helped co-found this Purdue this is the sort of stuff that we have over time started to work on in the ag space. I don't think I need to reiterate to this community probably all of the details of why open source is so important. But you know, as we looked at this space about, I think it's 6-7 years ago, and I just looked at my own personal life between being a farmer that wanted to make use of data and tech in agriculture and a software developer that wanted to make tech in agriculture. Both sides of that were a big pain in the neck. Like as a farmer, you can't do the stuff you want. And as a software developer, you've got to start from scratch. And so we got together and said, hey, the reason ag tech is so difficult, the reason that the promise of data has really been in agriculture is that it's the future. But that promise has been there for about 25 years. And so if something's been the future for 25 years, you kind of have to wonder why is it not the present? Like what's been holding it back? And you know, in my opinion, it's really the lack of open source. That when I have an idea to try out, there's no libraries, there's no stuff to start building on, or there wasn't then anyways. So that's what the open source or the Open Ag Tech and Systems Center here at Purdue is all about, to try to join that community here, you know, try to help bring some of the ag industry folks that traditionally might have been averse to open source to the table in this space, and really try to get things working for the development community. So we have some projects kind of at the point where I would say data starts, the sensors, machines, we have livestock apps, we do specialty crops, video processing, image analysis. We've got a pretty large group of professors that are all members of the center here that have a pretty diverse group of interests. Soils, water, environmental modeling, those kinds of things are also here. And one of our kind of flagship open source projects at that stage is IsoBlue, the brand you see there beside OATS on the left. which is an open source Linux-based telematics unit. So you can just, you can get the instructions for how to build one online, the bill of materials, you can put it together and plug it into any modern tractor, and it has access to the ISO bus, both the engine and implement bus on that, and it's got a built-in cell modem, so you can sync all that stuff to the cloud. And so that's kind of at the data source part, but we also have different IoT style sensors and things we work with as well. And then we do actually a decent amount of work kind of in the part of how that data ends up getting to the cloud somewhere. So the telematics, rural communications, rural broadband, that kind of stuff. And then kind of where we got our start, I think, in the industry most was really the security, privacy, / traceability space linked up with cloud APIs. So once you have data and you have a communication path, how could I push it up to a cloud over some kind of open source API and in ways that scale? And then all of that is useless if you don't have a front-end app or some kind of user interface to show people all this stuff coming in. And so the brand over there on the right, the Open ATK, the Open Ag Toolkit, was our kind of view or our vision for making the user interfaces that are these open source apps that can connect to your cloud of choice and solve some small problem or try to tackle one specific thing, like tracking antibiotic treatments for beef cattle or keeping track of field operations or something, that they sort of can play a role in a bigger ecosystem, but the app itself doesn't really try to do too much. And then all the way down through the real reason we started was we wanted to do machine learning and data science and things on the data that we had on farms from willing farmers, and we still couldn't get it. And so so the goal in that part is really doing the data analysis and helping develop the models and contributing to those things as well. And then as we got into it with the cloud API pieces, which was the Open Ag Data Alliance brand under OATS, that little blue circle, if you've seen that around, that we were contacted by a lot of folks in the produce supply chain to start with. And since it's expanded to protein, and I just now was starches actually this morning, but there's a lot of folks in the food supply chain, from retailers to distributors on down, that are really struggling with getting data moved across the supply chain between their systems. And it turned out that the solutions we had put together for the Open Ag Data Alliance worked there as well, but it needed its own brand. And so that's what Trellis is. Trellis is essentially our Open Ag Data Alliance APIs that I'll talk about later today, branded for the produce supply chain to help move food safety information and that kind of stuff between companies. And so that's the sort of gamut of projects that OATS works on at the moment. The thing I think that brings it all together is that our view of open source is that it really should be a tool that is used to build exponential commercial value through growing markets. That was the key thing the tech world figured out about open source years ago, was that you have much larger markets from which to extract value than if you try to go it alone. And so that's really our view of this, is that we don't want to oppose industry. We want to work with community. And so the sort of, if I could say, mission statement that describes a lot of the work that we've done in the last 5 years here, it's probably this one sentence, that what farmers really want from data is just that it should flow from wherever it starts to wherever they want it to end up without them having to manually touch it. That you don't want to go to one place's website and export a file and then import it into the other place and then have to do that every Monday morning or email stuff around. Like, you just want to get the answers that you're looking for on the farm without having to carry buckets of bits around all the time. And it's actually the inability to hit that part of the user experience is the thing that really keeps ag tech from finding the adoption on the ground that they had always dreamed of having. That essentially there's too much manual interaction from the farmer to get what they want out of it, because they're busy farming most of the time. And so if I could summarize that kind of in one word, well, actually I should say, we noticed that was what farmers wanted, and then we're ag researchers, right? So we have research projects running out at Purdue's ag farms, some of which are hours away from the campus. And it turned out that was the same thing we wanted from data as researchers too, that I didn't have to drive 2 hours to pull the USB stick out of the device out in the field. I wanted it to just start in the field and end up in my chart and MATLAB without me having to touch it. That's what I really wanted for it. And then turns out that's what the machine learning community wanted too, especially in ag. They were like, hey, we know how to do machine learning, but we don't have any data sets to run it on. So we need data, and we don't know a good way to get it. So can we just get the data to flow to us without a lot of work? And actually, if you think about it, and this is the thing that has sort of been a revelation to us as we got into this space, that's actually what everybody wants from data. You don't want to think about it. You actually don't want to have to mess with data. You just want it to work. And so that, if you want to summarize it in one word, that's what everybody wants from data, is automation. They just want it to end up where it has to without them having to mess with it. And so in our view, what would a sort of connection-based architecture look like in the ag industry amongst a lot of the different players, at least from a farmer's perspective, let's say, given that no one place is going to hold all the data that they're going to use for their farm. And so let's say I'm a progressive farmer here. I start out and I'm already got a telematics unit in my combine. Let's say it's streaming my yield maps to the cloud. That's great. I can look at them on my iPad. I'm happy. But it's really just confined to that one OEM's ecosystem. And then a startup comes along, machinehealth.com, and they say, hey, you know, if you could actually link us into that data stream coming off of the combine, we could actually tell you from our machine learning algorithms that, hey, I think that bearing's about to go out, or maybe this is some checks you should do on the machine because, you know, when we've seen these signatures in the past, it's been bad news, that kind of stuff. There's a few of those companies out there right now. And essentially, if that company relied on the farmer going to the OEM's cloud and exporting the machine data and then importing it into their web page, they have no business model, because no one's going to take the time to do that. So what they need is this sort of blue arrow. They need this automated pipe and this API connection back to the cloud that the data started at. And so that means that the OEM and machine health have to have some means of connecting themselves together. Then once the farmer has data kind of flowing in 2 or 3 different places, all of our own instincts are to kind of simplify the model, so I don't have to know the architecture. That I'd want to have the place where my data is at. And everybody that comes to me and needs to connect up and get my list of fields or something like that, I just point them there. So I pick a cloud of choice and I tell the others, hey, sync your data here that's important and pull your data back out of there as needed. And once I have that, now there's an ag data market. The ag data market is now I can buy a field sensor from one company and feed its soil moisture results into a benchmarking service that can tell me, hey, you know, other farmers that had soil similar to yours and had had soil moisture profile similar to this, you're like in the 80th percentile. So you know, you're doing fine. Don't worry about this. But in this other area, you're just terrible. And so maybe these are some areas you might want to focus some of your management routines on. Same thing, they might pull university data from somewhere, a recommendation service that would make prescription maps. You know, the prescription map needs to flow from my recommendation service to my cloud and then over to my planter. That probably is the same OEM as my combine. And then even more importantly, that like ag itself is primarily a logistics business in its day-to-day operations. So some kind of logistics management service that can interact with all these sorts of services is useful. And then I've got third-party service providers too that do stuff for me on the farm, like spread fertilizer, or every now and then they'll come and, you know, spray a chemical or something for me, and they generate data. They'd like to have access to that data. They do my soil testing, and you know, in this sort of perfect automated data world, they've got their own stuff. They don't really have to care that I have an OEM at the other end of my. And then these days, everybody talks about blockchain as well. And they usually put the blockchain in the middle of the picture. And I don't. I put it as one more destination for the data itself. And so really, even in a blockchain world, you still need some kind of an API connection back to the sources of the data that are supposed to feed into it. So if you take that picture and break it down into what are the basic components, that kind of how we see the world here is you've got API connections have to be there. They have to be cheap. They have to be ad hoc. They have to be easy to create and destroy. You need a or a services layer, or services at least, that if they're kind of inside your own company, you would think of it as a microservice. If they're outside your company, you could think of it as a service. And then you have to have storage and caching layers. Most everybody that's going to provide any kind of a service for you is going to need a copy of the data in their own platform so they can guarantee that it's up and running for you. Even to the point that they just provide a web app and you're caching that stuff directly in the browser for people. And none of that works if you don't have open source libraries, kind of like, you know, we have libtiff and libjpeg and these kinds of things. Like, you've got to have open source code behind the scenes here that provides the de facto standardization. Otherwise, you can never get all of these people to come meet in a room and all agree that that's how they're going to do something. And so it's really those four components, in my opinion, that have to exist to actually create the ag data market that everybody thinks is there. And so what we do is tackle that API connection layer, and we call that OATS Trellis. And what it really is an engine for microservice architectures that cross platform boundaries. Microservice architectures have become extremely popular in the enterprise world, in the web scale world for the last 5, 6, 8 years or so. But most of them all kind of focus on within our company's boundary. We'll have a bunch of services that interact, but then when you hit that company edge, it's very difficult to design those kinds of systems outside. And I think that's one of the things that Trellis seems to bring for the partners that we work with, is it gives them the language and the tools and the means to actually coordinate through code with the folks on the other end of that connection, even if the two of you have never met before. And that's actually a key point of this, is that in this picture, what makes it work is that the benchmarking service and the combine manufacturer never had to actually know each other. The important thing was that the farmer had data from a combine that he had to get to the benchmarking service. So as you start getting data here, one of the realizations that we had as we dug into the data that we had available was that data quality is a problem. I think most everybody can agree with that if you got bad data, you get bad answers. And the problem with farming is that because it's a logistics business, the quality of your data tends to be very time bound. So I've come up with this general formula that tells you how good your data is. The quality is proportional to the total value you're going to get out of the data divided by E to the T, where T is the amount of time before the user got the first value out of the data. So for example, I've been collecting yield maps on my farm for about 12 years, and I would take the data from the combine, open a Windows computer, import it into there, and then close it until next year when I did the same thing for about 12 years in a row because it was too hard to deal with it. And so it turns out then 12 years later, I want to do something with that data. So my time to first value was 12 years. So the quality of my data turned out to be terrible, because if you ask me, well, did you calibrate your combine, in year 7? I think I have no idea. And certainly when it was raining, I wasn't going to stop to go weigh a load of corn to figure out if the calibration on the combine was right. And so it turns out that essentially the quality falls off exponentially if you can't find some means to get that data valuable in the moment on the farm in the first place, and then we can derive all kinds of value out of it later. But if we can't find some way to make use of it at the moment on the ground, essentially we can't count on the data later being any good. And so here's an example. I've got cows on my farm. Starting in 2017, I had to record every antibiotic treatment that I gave to every cow. And I was writing it down in a paper book for a while, and that just takes forever. And if you've grown up like most of us have, and you type most of the time now, writing is kind of painful by hand with a pen. And so we were wasting a ton of time on our farm writing down records that, the next day when that calf came into the chute again, I wasn't going to take 10 minutes to flip back through that book and figure out when he'd gotten treated last time to see what he had. So I just wrote a little open source app here for tracking antibiotic treatments that is you type in their ear tag number to see what they've had historically. All you got to do is hit save treatment from that point, and you instantly get the record for that calf being treated and what he got. And so because the value that I get out of that data is immediate, it's while the calf is standing there and I'm trying to figure out what then I know that I've got an immaculate data set, because when I'm going to put the data in, I actually have a sort of immediate vested interest in making sure that it's good, because I know tomorrow when I go to look it up, I won't be able to trust it if it wasn't good then. So now I can do all kinds of great machine learning and AI on 3 years worth of antibiotic records and treatments, and which calves got better and which ones didn't, only because we were actually using all the data in the moment. Another example is I wrote that one and I said, hey, some of these widgets are useful, and I was weighing cattle going out the other side of our system. I weigh every single one individually, and I try to decide which ones I'm going to keep and which one, for another month, and which ones I'm going to sell. And we were sort of going by the seat of our pants based on how heavy the calf was. But it turns out that actually if you have a lightweight calf, but he's not gaining anything, then you probably should go ahead and sell him. But if you have a lightweight calf that's gaining really fast, I need to keep him for a couple more months and sell a different one. So I made this little iPad app that you just as we're running the calves across the scale, you type in their tags in with one cursor in order because they get funneled to single file. And it can operate independently of a second cursor that you're typing in the weights that are coming off the scale. Yeah, it'd be great if it was all Bluetooth and everything, but it's not there yet. But the nice thing is, as you type it in, you immediately get the rate of gain on that particular calf, how many days he's been here, and then you can decide whether you want to sell him or he needs to get on the truck today or something like that. And so because I'm using that in the moment to make the decision on whether to sell that calf or not, I also have immaculate records of weights and incoming dates and things like that going back for a while. And so that now that I made it useful in the moment, I've got data that is going to be really good for me to use later on. Another app that we made here at the OATS Center, open source, so those were both open source too, is we call the Fieldwork app. We're still working on this one. It's been through about 20 iterations. The idea was just to try to simplify keeping track of which fields you have done for various operations every day, and that's it. We'll just tell you, hey, you've got 57% of your planting done this year, or your second bean spray, or your burn down spray, or vertical tillage, or whatever it is. And it just shows all your field boundaries on a map, and you can tap on it and it'll turn it green or red or yellow, and then it tells you the totals at the top. But the key is that since I use that daily in the morning to figure out where we're going to go next on the farm, then essentially if I forgot to mark a field as done yesterday, I'm going to fix it the next day. So within roughly 24 hours, because I need to see I want to see the total in the morning. And so therefore, if I do it this way, I've got pretty good records about exactly which operations I've done when, and like which fields got cover crops put on versus which ones got deep tilled or something like that. And then if I'm trying to run an analysis later that would say, hey, what's the impact of deep tillage on my yield or something like that, I could have 10 years of good data to show for it because I knew I'd used it in the moment. So that's an example of kind of how we try to say, hey, if we want to figure out whether cover crops are great, well, I got to somehow give me a reason to collect all that data correctly in the first place. So when we get into the data space, kind of shifting gears here, I've noticed when you go to the farmer conferences and you ask them what they want from data, a lot of the times you hear the word interoperability. And what the farmer means by that seems to be, I don't have time to spend messing with anything. Pretty much it. Like I got this thing, I'm gonna plug it into my tractor and I should be hands off and I can go farm. All right, I bought this service and it just works and I'm done. I also go to a lot of the industry meetings where they set data standards and where the people try to get together to talk about interoperability. And it seems like this is what industry means by interoperability, is we all use the same data model and identifiers. And so to me, there's a gap here, which the difference between those two is the API connection. That essentially as a farmer, I still have to mess with it if I can export the file in some standard form, and then I still have to import the file in some standard form somewhere else. So what I really need is some sort of API connection layer that can move these standard forms of data around for me. And that's what OADA and Trellis is. And so I'm gonna kind of go through now some of the technical stuff because Ankita said we had some technical folks on the call, hopefully. So you guys are welcome to jump in and say, yeah, more technical or less technical, or let's see some code. But I'm going to stop there for a second and see if anybody has any questions on kind of the overview stuff first.
I think you're doing great. Keep rolling.
All right. Okay, thanks. So we'll dive in. So the basic idea with OADA and Trellis was, all right, you have to design an industry standard API framework. Go. Like, how would we do this? What are we going to do? Well, it was very obvious up front that the one thing you could not do was create an industry standard data model, because that's the thing that everybody standard data model competes with version 1 of your standard data model. And so we said, look, what we really need is an API that says, regardless of what data model you have, we'll take care of making the pipe. It gets the data from A to B and tracks changes and helps you discover it and do service discovery and authorization and things like that. So if you look at existing REST APIs that are out there, I mean, most folks have REST APIs. That's kind of the standard for how people are going to deal with interacting with servers these days. They have some basic concepts that, they were outlined by Roy Fielding in his thesis back in 2000, but the gist of it is generally you have things called resources that are just a generic connection of bytes. A resource can be changed, so it's versioned. And you usually identify it with some kind of unique identifier, and on the web, those typically are URLs. And so if you look at a URL for almost anybody's API that I've ever seen, it tends to look like this: hostname / and then some other stuff with slashes. And if you say, what does that look like? Well, it actually looks like a file system, right? Like it looks like you've got a drive folder, and in there's a U folder, and then there's a 0 folder, and there's a folder named folders, and under there's a 0BWMD whatever folder. And then, you know, that's not by accident. That's how the web used to work, right? We all just ran Apache, and we put all of our stuff in there in the folders, and it would serve the proper things. And so a file system is a graph. So it means that essentially the bulk of the world that has to move data around represents their data as a graph, at least from an identifier standpoint. So if we standardize around that, we shouldn't have to worry about too many people disagreeing that, no, we don't want to use URLs and file system-like names for things. And so that was kind of where we started. We said, hey, the thing that's missing then is how do we define a link between two resources within the API framework? And there's some things called JSONLD and a lot of semantic web ontologies and things that are out there that essentially create stuff that doesn't look anything like what you would make yourself if you were just making a REST API for your own project. So what we wanted to do was try to create some form of a link that can give us this file system like graph, but it actually looks like the kind of stuff you would put in your JSON documents anyways if you were making a REST API itself. And then I think how it kind of flushes out in the end is you can look at it like, imagine that you had a set of 3 farmers that all had the same agronomist, and that agronomist had a piece of software that he wanted to point at your data that then would look at it and come up with your prescription maps for planting, let's say, and put them back. Well, the idea of having a standard API means that, or at least a set of standards to choose from, would mean that it's sort of like they all agreed to use Google Drive, so that we had the API calls down, and then inside their Google Drive, they all had this sort of managed folder structure where they all agreed there'd be a fields folder and a harvest folder and a livestock folder, and then under that there'd be, you know, other things, so that when he connects his software to all their Google Drives, it knows how to just go find the particular pieces of data that it's looking for because it has a semantically defined graph. And so it doesn't mean actually that they all have to have the same graph. It's easier to understand that way, but it needs to be a sort of discoverable graph, at least, that, you know, there's one of like 10 different graphs that people tend to use in the industry, and my code knows how to figure out which one you got and find the data it needs in the 10 different forms. And so the graph structure itself, I'm going to kind of go over the thought processes you need to have to do these kind of graph style data modeling problems. It's got a lot of roles. It's got a semantic role, a sharing role. I'm going to go over each of these kind of in detail here in a minute to give you an idea of how you would work with the OADA and Trellis API itself to actually represent and serve your data. So the first one, the semantic role, was kind of what I showed in the Google Drive folders, which was just, it's like categories of data, right? That it has the folders themselves, or the folder names, you can think of them, have a sort of meaning to them. So each resource has a fields key in it. And what you mean by that is all this stuff about fields is generally under this key. Like if you're in the domain-driven design community, these top-level things tend to be like your aggregates. But like maybe under harvest, then there's other semantic things, like I have as harvested data and I have other kinds of stuff under harvest. And maybe under as harvested data, there's yield maps. And so one role the graph typically would serve is just in figuring out or separating those categories of stuff from each other. Another role that the graph would make, if you're trying to come up with this folder structure, is for sharing. So if you had an agronomist and you only wanted him to, you were going to give him yield data, but you only wanted to give him 2018's yield data, then you probably want to group your yield data into years, like put a years folder on there in 2018, and then share just the 2018 folder with that guy. And then he doesn't have access to all your past yield, but he has access to the stuff that he needed for just that year. So you'd use it for both semantic and for sharing in that case. But of course, the problem you have, and you've had this if anybody's ever shared their Google Drive folders with you in the past, all the semantic information when you shared the particular node. And so that means that one of the things that Trellis requires you to have, or OADA requires you to have within the API, is you have to, every resource has to have a content type, and the content type is not JSON. That's a serialization. The content type is, this is an as harvested yield data file defined by ISO version 1 or something like that. Like it says the kind of data, the type of content that is in the thing, so that when you get it, then you know the semantic stuff is, oh, okay, no matter where this was in the graph, I know it was a yield map. And additionally, you may have something, what I call a traveling context, that you may want to just put inside of the 2018 resource that, hey, this is actually from the 2018 year, and not just a generic set of yield data. And then there's other times actually that a filtered graph is a better fit, that I want them to have 2018's yield data and 2016's yield data, or maybe just all the corn data. And it's really hard to come up with a graph for every possible scenario. So you may want to just go ahead and create a sort of purely functional filtered version of the original graph that just has the stuff in it you want. Keep that in sync and share that. The third role that we have with this stuff is indexing. So if the resource that you're getting to, like let's say that under 2018's yield data, you had a CSV file and it was just all your data points, the time it was taken, latitude, longitude, your mass in that area, moisture, that kind of stuff. Like if there's only 13 rows in that points file, then you really have no problem with indexing. It's not a problem. You just that's your API right there. You go to points.csv, you'll get your 13 rows back, no problem. If you got like 130 million rows though, like I've got 10 years of yield data, suddenly this is a problem. And that's what databases are for, right? That we would say, hey, I don't want to pull back the 25 gigabytes of data just to be able to draw you this one map tile on the screen. I only need the stuff inside that map tile. And so, the typical way a database would handle this, and the way people would do it with normal REST APIs, is it'd build an index like this, right? It'd have a thing that says, here's all the latitudes, and this latitude corresponded to that ID, and this latitude was that ID, and so on. And then we'd sort all the latitudes up. So then it was super fast. If you asked me to give you just this little latitude window, I could, almost immediately give you back just the rows that you need out of that original data set without having to look at all the data. And that's really what indexing is about. It's how you can find some things without having to look at everything. And so people would do that in the REST APIs like this. Typically, they'd add query parameters on the end, and they put the question mark, they give you a variable, latitude equals this, longitude equals that, and then it'd pull back everything that, let's say, had that prefix of latitude and longitude on it. Which really means they just took that, stuck it in a MySQL or Postgres query usually, and then gave you back the result. But the REST guys were we're looking at this and saying, well, wait a minute, every resource needs to have a uniquely a unique URL to identify it, or it doesn't really adhere to the normal REST principles that let the web scale. And they said, well, actually, that's the exact same thing if you had just taken the query parameters on the end and dumped them up inside of the graph structure in the front, right? We just said there's a latitude folder, and under that's those latitudes, and there's a longitude folder, and that's the longitudes, and then points.csv. So we kind of took that approach as well, that we didn't think an industry could come together around a group of thousands of query parameters that might be allowed on the API. So we said, look, that really should just all be baked into the graph directly. And actually, it turns out that that's an index too. But what you see here is really how you index stuff in a graph. Is you split the graph at every stage where the number of things at that node is going to get too big. You split it into 2 nodes, or you split it into 10 nodes. And the identifier for the node is something about the data that's inside the node. So it's all of 2018's data. And if that's too big, then we split it up into spatial groups or something like that. And so that might look something like this in a normal API you'd find in ag systems today. There'd be a 2018 year and a set of fields, and then there's the back 40 and the front 40, and then you get the points themselves. And when you did that in your API, you actually have, usually most people were not aware, but they had graph indexed a large data set into smaller buckets. But unfortunately, this is how the ag industry did it, and they all committed a cardinal sin and broke the world. That this essentially is what makes data such a hassle to deal with in ag, is that they indexed the entire data set by a completely arbitrary name that I happened to assign it on the day that I harvested it. And so unfortunately, when you're indexing things, picking arbitrary things that are not unique and can change is typically a terrible idea. And so if you're going to index stuff, you're always got one place the data has to go first. So rather than making it a name the farmer came up with, we have this terrible acronym graph structured OADA delivered geohash index and time index data, GOG-T, which just because when we wrote that paper, we couldn't come up with a better name on the spot. So it is also acronymized as an acronym in search of another acronym, or ASOAN. And so how that manifests itself is, let's go back to that latitude longitude piece. I mean, most of you that have ever tried to set up folder structures like this on your own machine probably recognize that, wait, it's arbitrary whether I put latitude first or longitude first. And yes, that is the fundamental problem of geospatial query, right? that we've got a two-dimensional thing and we want to get it down to a one-dimensional thing to do all of our searches by. And so it turns out there's this really handy tool called a geohash. If nobody's seen it, I love it because you don't have to project the data first. And essentially, we can group all of the data into tiles. And each tile has a unique name for that tile, effectively, that comes from this. That if you have a latitude and longitude, and you just take all of the bits and you interleave them. So I did it here in like base 10, but in the normal geohash, you interleave them in binary. You end up with a number that actually is what you want for an index, that points that are close together in space tend to be close together in number. And it's purely functional. So if I know a latitude and longitude, I know the exact geohash that goes with it. And if I know the geohash, I can pull the latitude, longitude back out. And even better, it's composable. So if I mask off a certain number of bits in the geohash, I'm actually defining a complete set of latitude and longitude points because it's all the latitude, longitude points that started with that particular set of numbers. And so the geohash standard itself says, hey, take these things where we interleave the numbers and then turn them back into a character string. And then depending on how many characters you pick, that defines the size of the tile that you have. So if all the data on the farms that we were going to go access was actually stored this way instead of stored under their fields, making it impossible to sync data between two different platforms, we wouldn't have that problem because this is reasonably immutable, at least on geologic timescales, right? The plates don't move that fast. So like that spot on the Earth is that spot on the Earth, at least for a little while. And then hey, if I'm looking for the stuff in this area, you can pick the area size that you want. And then go find all the tiles of whatever size it is. And all you knew was, I just want everything that starts with DP 69 at the front or something like that. And so the time index part is like, here's the geospatial index of all the stuff that happened in 2018. And here's the geospatial index of all the stuff that happened in 2017. And so how that looks on the globe, like if you took all the latitude, longitude points on the globe and charted them out, it would look like this. Everything that starts with B is in the top left corner, and the US is kind of splitting 9, D, C, and F. And so then I see that the question says, unfortunately, magnetic south is actually moving a few kilometers every year, so the Earth is breaking everything. We did think about the fact that geohashes don't work great near the poles, but we also decided that we don't grow a lot of stuff up there either, so at least for ag perspectives, as long as we're not harvesting snow, it'll probably work. So anyways, if you zero in on D, then like you get a latitude longitude whose geostat starts with DP, it's entirely within that little region there. And then if you get a 7-character one, that 2.5-acre tile, like it's in that little section. I think that's one on my farm or in Lafayette here, one or the other. So that's kind of how it looks. So we get all these great properties for indexing from it, that it's a 2D to 1D transformation. It's approximately immutable. It's completely unambiguous, purely functional. Fewer bits tends to mean bigger tiles, and close in number tends to mean close in space. So we've had a lot of success interacting with the data this way, because once this was in a REST API that it represented it this way, then you actually could enable every web app that was connecting to inherently ask for just the data that it was looking for. So an example of one that we made was called Trials Tracker. This one is really cool that it actually can have yield data behind the scenes in an OADA cloud, an OADA conformant cloud that uses the OADA API. It indexes all by time and crop and geohash. And you can actually move around this map and not have to tell it what fields you're interested in ahead of time. It just loads the appropriately sized tile, but it doesn't load in like a JPEG of it. It loads in the raw data as JSON and renders it all behind the scenes to a canvas in the browser. And it caches it all. So it's super fast and you can run things offline. But the coolest thing about it is because you have that inherent geohash structure, we ran a service behind the scenes that computed the total sum of all of the yield points and all the mass and all the area for every single tile. And so it means that when I draw or request in order to compute the actual average in that spot. So we actually were able to create a mobile app here that you can have yield data for the entire United States and draw a polygon around the eastern half of it, and it can tell you the average in less than a second, which I think is pretty cool. So the goal of Trials Tracker was during the season, as weird stuff happens, you just write it down and draw a polygon. And then as you're harvesting, the data from your combine streams into your OADA cloud, and then it can tell you the averages while you're actually out in the field. What 3 words I see from Ankita? I just saw that like a month ago. I love what 3 words. It's actually my kid's favorite game to play on my phone is look up a random tile and then laugh over the 3 words it picked. So yeah, what 3 words is awesome.
I guess so. I was even thinking that if we were thinking about this idea of human readable URLs, that it might be a useful way to go around, you know, as opposed to having to remember DP69WHE, it would be potato book pot.
Yes. Well, the problem with what 3 words is that it's not this reversible, purely functional thing. You need to have the mapping behind the scenes of how I get to the word from the latitude, longitude. So it's a little harder to interact with. Like that's why you pay them to have their API to tell you what the words are. But it's still cool. It's a similar idea. So anyway, I think GogT is actually a great option for a lot of ag-related data. If this was sort of how we stored the data at the USDA for LIDAR and weather stations and soil tests and anything that's out there, it just dramatically simplifies interacting with it because it's just so obvious how to get the information that you're looking for. And like I said, it's pre-projection. So it's not like you then have to say, well, I'm in UTM, 16, and then I'm in that space. And now I need to convert to this other space. Like it's just the latitude, longitude points originally. Yes, I know in some datum, but still it's how it originated. So then role number 4, the 4th thing that we have to do with this graph is all the hard stuff. I lumped it all into one role, but each one's kind of a role itself. Streaming, updating, versioning, concurrency, all the fun stuff. So let's just focus in on one part of this big picture that I said, which is sort of like yield data, just going from the combine to my OADA cloud that was serving Trials Tracker or something like that. If you think about that, you can look at the resource itself as what we coined an ordered stream of idempotent merge operations. And so what that means is if I look at the document down on the right there, right here, that may be the initial state of this JSON document that contains my yield points for a particular geohash tile, and my combine was kind of pushing them up there, and they all got merged into this array of data over time. And maybe it has the sum of the points and the count and the number of things in it, and that was version 1 of the document. I did a put to that thing with all the initial stuff. And so then my cloud of choice synced that over beginning, when I first made the connection, it goes and gets all the stuff to keep a cache of it. But then it would rather not have to resync over gigabytes worth of data every time I pushed one new data point up to the cloud from my combine, like an IoT model. So what it would rather do is after I got the first version of it, I'd like to just get the change stream after that and apply the changes to my document at any point outside of that. And so that's where the ordered stream of idempotent merge operations comes from. Is idempotent just means that if you apply the same thing over and over and over again, you'll get the exact same result, kind of like the save button in Microsoft Word. Like you push save there and you keep pushing it, you'll have the exact same set of bytes on the file if you don't change the file in between. But if you push save as and you keep picking new file names, you'll keep getting new stuff. So that would be a non-idempotent operation. Versus idempotent is I just keep doing the same thing over and over, I get the same result. Each of these change documents is actually just the sort of sparse JSON tree that you would merge inside of this resource to end up with the net resource being the same as it was after version 1 for anything. So in a sense, only the parts of the document that change come through in a little tree, and you can merge them directly with just a normal JSON merging operation if you want to. And handy fact, because ag is inherently a multi-master synchronization environment, that the merge of UUIDs, so if the data here is not an array, It's actually an object that just contains random keys for each data point. Then when you merge them between as many different clouds as you want, they will gradually converge to all of the same answer and nothing gets overwritten, even though it's all idempotent merge operations. So that's kind of a cool property here. That doesn't matter how many combines are pushing data up, that as long as we design the data model correctly, they all sync without us having to do any hard work, which is good because hard work and synchronization is really hard work. So then within OADA, you can create these things called versioned links between the different nodes that we have in our URL right here that says, hey, whenever the thing below me changes, I want you to include its rev or its for. But if the parent document had a versioned link to it, then the underlying OADA system will update the rev on the parent document eventually. It's not instantaneous. And then since its parent document had a version link to it, it'll update that. And then we had a version link to 2018, so it'll update that one. And so that means you can watch 2018, the 2018 node by itself and actually get streamed all the changes that happen to any part of the subtree within that graph. So that makes it substantially easier to connect up and watch for, like, I just want all the yield data from this guy. I don't care about spraying records and things like that. And you can do it all client side. You don't have to coordinate with the server ahead of time. The next thing that you have, or actually what I just said was you can watch the node for changes. Because the change stream you're going to get is this ordered stream of idempotent merge operations, then you can actually just replay the OSIM stream at the remote side, even if it's not the same resource. Like you can actually have a resource at one node in the network that merges all the streams from other nodes in the network and gets a composite document, which is kind of handy. The other thing that's pretty important if you're dealing with, you've got to handle with concurrency somehow. And so the revs themselves, you can actually pass headers to the REST request that says only execute this write if the rev is still 4 on the document. They call that optimistic locking. So that's a way that you can guarantee you don't accidentally overwrite somebody else's stuff. Is you basically have to keep a cache of it. And then the last time I got a copy of it was in rev 4. But this brings its own overhead for the server, though, because it eliminates certain server architectures that you can have. It forces you into a sort of DynamoDB model where like you can have, when you're going to scale, one node has to be responsible for a particular resource because it has to know what the latest rev was. We can't have an eventually consistent backend that for any arbitrary resource, we never truly know what the last rev was. But it makes writing the client substantially easier than the alternative. So then the next thing, we've got a library that we've been working on this year that is OADA cache entirely in JavaScript that you can just drop into any web app that you want. We like to use React in a library called Cerebral, but there's also a vanilla JS version of it that it'll basically let you send these requests off, set the watches on the nodes for you, maintain a cache in local storage, and then stream you the changes to your app on top of that. But then it'll also have the caches of everything behind the scenes and just handles most of that overhead behind the library. So that's kind of handy. So you might have noticed that we have too many requirements for one graph structure to solve them all. And this is kind of the headache that you run into with graphs, is that you want it in 10 different ways. And that's what SQL databases were great about, but we're not going to get the entire industry to agree on what the proper table format is for all ag data for all time. And it turns out that that's actually a pretty common thing with data modeling. That, like, I don't know if anybody else is a domain-driven design fan, but I'm a huge Triple D fan, and not diners, drive-ins, and dives. Actually, I like that too, but domain-driven design. And the best quote from this entire book was on page 332, in my opinion, which was total unification of the domain model for a large system is not feasible or cost-effective. Meaning, and of course I say, and that's okay. Like, that's what the Triple D community is about, is the fact that how do we deal with the fact that that statement is true and still build large scale systems? And so the thing they came up with was this idea of a bounded context, that if you can't bound the problem you're working on, you'll never solve it. Or I'll give you an example that the industry did get together in ag a long time ago and came up with this idea that all farms and fields that a grower has should actually be represented in this data model that's a 3-level hierarchy. Yeah, all right. And we've got a couple of minutes left, so I'm almost done. This 3-level hierarchy they called grower, farm, and field. And they did that because they were writing software for co-ops that had a lot of farmer customers. And so they said, hey, well, the co-op would want to store everything under a grower, and then the grower has farms and fields, so we're good. But of course, then the farmer's tractor has grower, farm, and field inside of it, because that's how the industry decided to represent farms and fields. And he doesn't know what to put in the grower key. But you can't access the farm from the farmer unless you have the grower that it's under. So then when he gives his farms and fields to the co-op, it already has growers there. And guess what? It's not their name. It's like the landlord for that field or something. So then the co-op has to have yet a fourth layer, like the client, grower, farm, and field or something. So in other words, there isn't one right way to do it. And when you cross these boundaries, you inevitably have to translate things. You cannot share the same model because it doesn't work. And so the formula I put together for how I think this is that the probability of your project actually succeeding is proportional to 1 over the area of the context that you're tackling. So the more you can focus the problem, need different read models, or why there isn't one correct model, is from Eric Evans, the writer of that book. He gave this in a YouTube talk and I loved it, so I started putting it in a slide here. This is a Mercator map made in the 1500s, and most of us have probably seen this at some point in time in our life. We probably learned it in school. And you could ask, why is Greenland so enormous? And one answer is that Greenland was where all cartographers originated, and they had a high sense of themselves, and so they made their country look giant. And essentially, it's a conspiracy against the world to make Greenland look more important than it really is. I mean, even Trump wants to buy it, right? So maybe it's because of this map. So the problem is, if you're trying to look at this map to get an idea of the relative sizes of countries, this would be a terrible way to look at the data. But if you lived in the 1500s and you had to navigate the ocean and you wanted a map where you could draw a line from any point to any other point and know the exact heading that you had to set your ship on to get there, this would be a very handy map. So it's not that like this is wrong or right, it's that for the use case you have, this is how you need to index or read the data that you're looking at. And a different use case fundamentally has a different way they have to look at it. And so the industry itself came up with this sort of microservices model that said, let's embrace that. It's okay to have copies of stuff. Use the tool that fits. Like if Redis is the right database for this part and MySQL is the right database for that part, write a syncer that keeps the two in sync. And even they've even gone to the point where they all like to have this sort of database per service rule, that every service has its own individual database, and they all just subscribe to an event queue. And it doesn't mean that you have like one service per bounded context. Usually it's sort of several services within one context, and when we need to move context, then we translate between them. And so this picture, I think, can be understood in those terms. We've got the pipes that get the data from A to B, but the data models themselves inherently are going to need some translation between company boundaries. Like as you cross a company boundary, you're going to shift to a different data model no matter what. So we just need to kind of embrace that that's the nature of the beast, and have open source libraries and translators that can run as microservices within this sort of an ecosystem. And then it's really not a headache. Like they're just purely functional transformations. And so if you ask me, that's why data standards generally fail, data model standards. If you try to solve all problems for all people with a single standard data model, you created a context boundary that's infinitely large. And therefore your probability of success is 0. And that's why most of these ag data standards projects tend not to work in practice, because they make things that are too complex for any a developer on a particular project to pull off. So I'll leave you guys with my favorite thing right now is event sourcing. I'm really excited to see that coming through to ag, and I'll leave that as a thing to look up and maybe entice you to keep talking with us later. So that's it for me. And we're just 2 minutes. We got 2 minutes left. So I guess we got 2 quick questions.
I have questions.
Well, if no, okay, go first, Greg.
I always have questions. First, as a non-developer of backends, but a frequent user of backends, that was like watching you describe your backend stuff was like learning like central limit theorem, like in college. It was like, so thank you for that. That was fantastic.
Hopefully that was a good thing. Like, yeah, it all just reduces to the Gaussian. That's what it is. Backends are all basically Gaussian behind the scenes. No,
it's fantastic. Now I feel like now I am like empowered to go into the world and look at URLs and be like, I know what the fuck that means now. So that's great. So I had several questions, but I'm gonna just ask one. You have this really nice description of the interaction between all these components in sort of the ag tech world, and you described how to sort of format the pipes between them, and where there's a limitation of how much you can format those pipes. What I think would be so cool in the context of Open Team would be, especially after Denver, when everyone kind of knows where everybody else is, and we can kind of map out what, again, we're not defining the canonical, but we're defining a set of things within that space. For you to look through and say, here's the areas where the communication between services is doing well, and here's the areas where we could use something like OADA to standardize in a way that makes sense. Because I'm sure there's areas where people are doing things well, and there's areas where we're doing things poorly, and that when we look forward at what we're going to work on for the next year, like, where should we be using those standards? I think that just mapping that for people would be fantastic.
Great. Yeah, I think we've got 2 guys set to come
Yeah.
to Denver too, right? Right, Ankita?
Yeah, I was going to say that part of the reason why I'm really excited that we have 2 students coming with me to Denver is because their goal really is going to be able to get a better sense for what everyone's doing and try to think through the mapping of different. Aaron, perhaps you could point us to the GitHub repository in a couple of different spaces where people can go to actually access some of the stuff you've been describing, so that if people want to play around with anything in the meantime, whether before Denver or after. Yeah.
GitHub.com/OADA, OADA.
There was a really lovely tutorial that you had walked me through when we first met. Would you be able to point us to that specifically?
Absolutely. So under OADA, there's a lot of repos, and we put all of our docs under one called OADA docs.
What a beautiful URL that makes.
Yeah, so if you go to the beautiful index of OADA docs and you scroll down to the README up here at the top, there's an intro to the API presentation flavored with Trellis that kind of goes through a lot of the technical details I skipped over today.
Yeah.
It's intended to be kind of an introduction to this REST API spec and how the things work. And the other piece that's important is there's one repo that actually implements the REST API spec as a set of Docker containers that you can run yourself. Like, you can just clone the repo and do docker compose up-d, and voila, you have a running instance of the OADA API on your machine. So that one is OADA Service Docker.
Thank you. Yeah, I know if anyone either listening in to the webinar later, or is anything like me, it requires just being able to sit down and actually walk through some stuff for a lot of the ideas to really sink in. So I think this will be hopefully helpful for everyone to be able to play around with OADA and think through how they might want to engage.
Right.
Any other questions? Cool. All right. With that, I wanted to say big thank you to Aaron. And I think that's all we've got for today's Open Team webinar.
Okay, thanks, guys. I'm excited to get to know more about what you guys are doing, and maybe bringing our communities together here too. So looking forward to how that goes. And Ankita is going to be our bridge. We're going to walk all over her.
Oh boy. Oh boy. All right, guys.
All right.
On that joyous note.
Yeah. Thanks.
I'll see you all in person and on the internet.
Thanks. Bye.
Hello? Oh.